Hello, AP Calc. I'm going to go over Chapter 2, Chapter 2, Section 2, Part 2, Limits Involving Infinity. In the first part, let me adjust the camera. It's a little to the side there. Actually, that's a little better. So in the first part of this video, in the first part of this section, we talked about limits as x approaches infinity, as x approaches positive infinity, and as x approaches negative infinity, that being as x goes very far to the left for negative infinity, and as x goes really far to the right for positive infinity. In this part, we're going to look at what happens when x approaches a number, but the value we get from that limit, I shouldn't say value, but the answer we get is infinity. And we're going to go back to this graph 1 over x. I said last time that this is a very nice graph for this type of looking at infinity, because not only does it have a horizontal asymptote here, where as x approaches infinity, this function goes to 0, but now we're going to look at this right here, which is a vertical asymptote. So we're going to try and find the limit as x approaches 0, so that's this right here, from the right, so coming this direction, if you can see my mouse here, coming this direction. And to do this graphically with the table, I'm going to go into, my table's probably all messed up from the last lesson. Yeah. I'm going to set this to 0, and I'm going to change the table set to 1. So it's just kind of like the default table set. And if you look at this, I'm going to just go up a little here so I can see this. This is from the left. This would be from the right. Okay. So really, I just need to look at the stuff below 0. And you can see here that it's 1 and then 0. So we're not getting a very deep, minute look at what's happening as it approaches 0, because 1, increasing by 1, is actually a large increase for what we're looking at. So going from 0 to 1, I want to look at the numbers between 0 and 1 is what I'm trying to say, not the numbers from 0 to 1. So I'm going to go to the table set, and I'm going to change this table change to 0.1. I'm going to leave the table start at 0. Okay, so now what we can do is we're looking closer at the values. We're looking at values closer to 0, because now we're looking at 0.1. Okay, and now we're getting closer. And you can see that as you get closer to 0, which would be coming in this direction, going up this table, the values are getting larger. But it might still not be quite close enough. So let me change the table now to 0.01. And now we're going to get even closer to this table. And what do we have? Well, wow, we are even getting higher now. So as we continue to get closer to 0, these numbers continue to grow. And we could keep doing this and getting closer and closer by changing the table scale, or the change of table value. And now we have 1,000. So this is an example of the numbers getting very large as the x value approaches 0. So we would say the limit as x approaches 0 of 1 over x equals infinity, because this is just going to continue to grow. This is just going to continue to grow as we get closer and closer to 0. This is just going to continue to get higher and higher. The same is going to be, something similar is going to happen for the left side. The limit as x approaches 0 from the left side. All we need to do is actually go back into this table and just jump up here. And the actual scale that we used of 0.001 is still being used, but now we're looking at it from the other side. And you can see that the numbers are getting very large, but it's going to be in the negative direction. And that's what it looks like when we approach negative infinity, that we get, as we get closer to 0, what the limit's approaching, these numbers continue to get larger and larger. They're not approaching a number, they're not ending. So if we would get even smaller change between these two values, we would get even larger numbers here. So the limit as x approaches 0 from the left side, will go to negative infinity. And this will actually give us our definition for vertical asymptote. The real math definition for vertical asymptote is that a line x equals a is a vertical asymptote if the limit as x approaches a of f of x goes to positive or negative infinity. Remember, a horizontal asymptote's definition was as x approaches infinity, the function goes to a number. The vertical asymptote definition is as x approaches a number, the function goes to infinity. One note to make is that the limit as x approaches 0 does not exist, since negative infinity does not equal infinity, by the way. Vertical asymptotes, so a note to make is that when you try to do direct substitution in a polynomial or a rational function, if you ever get a number over 0 when you plug in, not 0 over 0, but something other than 0 over 0, 0 over 0 is removable. That's a whole. A number like 7 over 0, 100 over 0, this would be a value that a vertical asymptote occurs. This is something that is true for polynomials. Not all the functions we look at will be polynomials, though, and won't always be able to easily do direct substitution. So if the bottom being 0 is what causes vertical asymptotes, when we're asked to find vertical asymptotes of a function like this, there might be, or if there is a vertical asymptote, it will be where the denominator causes, where you get 0 in the denominator, where there's a 0 in the denominator. So what x values cause 0 to be in the denominator here? Well, you can set the denominator equal to 0 and solve, and you'll see that 2 and negative 2 plugged into this will give you a 0 in the denominator. So they might be vertical asymptotes, they might not. Like in certain situations, doing this might give you something and it may not be a vertical asymptote, but there won't be a vertical asymptote anywhere else. Does that make sense? So this will give you points of interest, is what I'm trying to say. To determine whether or not they're vertical asymptotes is actually pretty easy to see that they are going to be vertical asymptotes, because when I go to plug in that value, negative 2 I'm going to start with, I get a 1 on top, because that won't ever be anything but 1. So I will have a non-0 over 0 for both of these, indicating vertical asymptotes in this case. But if I would plug in and get a 0 over 0, then it wouldn't be a vertical asymptote, even though we had a point of interest there. I'm hoping that makes sense. I don't think I show this graphically in the notes. Oh yeah, I do. Okay, I do. But I can put it on here anyway. I'll type it in so you can see me type it in. 1 divided by x squared minus 4, zoom 6. This is what it looks like graphically. You can see here's negative 2, and right here's positive 2. Vertical asymptotes. Now, whether or not they go this up here, the part up here, without looking at it graphically, we won't know just from this algebra that we did up here whether or not the limit goes to positive or negative infinity. We'd have to look at the table or the graph to see what's going on as far as whether the infinity is positive or negative. But it didn't ask us that in here. It just asked us to find vertical asymptotes. So you can see here from the graph that the limit as x approaches negative 2 from the left goes to positive infinity. Negative 2 from the right goes to negative infinity. 2 from the left goes to negative infinity. 2 from the right goes to positive infinity. All right, are you ready for one more? And then I think these notes will be done. Find the vertical asymptotes of the graph of cotangent of x. Cotangent of x, there's no cotangent button, just a reminder. So in order to do cotangent, we'd want to do 1 minus, well, there's a couple things you could do. 1 minus tangent is what I'm going to do. You could also do cosine over sine, cosine x divided by cosine x. So let me just do a zoom 7 here, because it's a trig function. And here we have the graph of cotangent. So vertical asymptotes will occur when tangent is equal to 0, because 1 over cotangent is 1 over tangent, and when tangent is equal to 0 is when we have over 0, 1 over 0, So again, it'll be a number over 0, not 0 over 0, a non-zero over 0, I should say, because 0 is a number, so I can't just say a number over 0. So a non-zero number over 0, causing vertical asymptotes. They will occur whenever tangent is equal to 0. What values of x cause tangent to go to 0? You might remember that that would be pi and so like this would be 0, this is pi over 2, this is pi, this is 3 pi over 2, this is 2 pi. Okay, then go in the other direction, this would be negative pi, this would be negative 2 pi. So it looks like it's going to occur anytime that tangent is equal to 0, will be every pi, every factor of pi. So we could say this by saying x is equal to k pi for k in integer. So we're making it k only integers, so k can't be 1/2, it can't be 0.4 or anything like that. And then anything that meets this condition, so pi, 2 pi, 0 would work because 0 pi is 0, negative 1 pi would be negative pi, negative 10 pi, 100 pi. All of those values would cause a vertical asymptote for cotangent. And that's because tangent is 0 every pi. So let me just show you one thing here. If we go back to the normal tangent function, okay, graph this. Remember, see here, anytime this function here has a 0, is a 0, so it would be here, negative pi, here 0, pi, 2 pi, negative pi. So those are the points that tangent is 0. Those are the points that cotangent would have an asymptote. And that's it for this video, a little bit shorter for vertical asymptotes. So thank you and good day.